तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Again, we will look at error propagation and the effects of finite representation of floating point numbers on programs and the results we get from programs. Last class we had looked at error propagation in functions of single variables, and we said what we mean by this is that if there is an error in a variable x, and then what is the effect of that error on the function f of x. As x is a floating point variable. Now, that is represented on a machine using a finite number of digits, and because of that a function which depends on this variable, a function of this variable, would the numerical value we get from this function would depend would have some error. So, now the question is, how does this error in x propagate into that? That is what we looked at, and we said that if you assume x tilde as an approximation to x, that is x tilde is the finite machine floating point representation of the actual value real variable x, and then what would be the effect of the discrepancy between x and x tilde on the value of the function. That is what we have looked at. Or we have to estimate delta f x tilde, that which is actually the difference between f of x, the real variable x, the actual variable x, minus the floating point variable x tilde, f of x tilde. We are not interested in the sign, so we take the modulus of that. So, that is the estimate which you have to make. So, what we did was we could assume that x tilde is close to x, the real value x, and we could expand f of x tilde around f of x, or f of x around f of x tilde. So, f of x is the real value which you want, and we are saying x tilde is and x are very close to each other, and we know that when a function, if you want to evaluate a function which is close to some other to a variable which we know, to a value which we know, we could expand that function in a Taylor series around that, which is basically a series of derivatives of the function. So, here we assume the function to be a continuous differentiable function, right. That is important. So, if you have a continuous differentiable function, and then we could write f of x as f of x tilde plus f prime, which is the derivative of f evaluated at x tilde into x minus x tilde, that is the delta x, and then the second derivative which I written as f double prime divided by 2 factorial into delta x squared plus f third derivative. So, this is third derivative again evaluated at x tilde. So, this notation here is f of x tilde means f evaluated at x tilde, f prime of x tilde means f prime evaluated at x tilde, and similarly all derivatives. So, you could expand this in the series. We are only interested in this particular calculation only up to the first order. So we could say f of x is f of x tilde plus f prime of x tilde and x minus x tilde, which is our delta x. So from here you can see that I can make an estimate of what will be the f of x minus f of x tilde how does f of x minus f of x tilde depend on x minus x tilde, and you can make an estimate of that, and you can see that it will be proportional to the derivative, the first derivative of f at x tilde. Okay, so that's what we wrote it here as. Okay, so that's the estimate you will have, f of x minus f of x tilde approximately equal to f prime of x tilde into delta x. Okay. Or the error which we originally want to estimate is delta f of x is f prime of x tilde into x minus x tilde. Okay, so that's what basically we get. So you say if the derivative is large, then the error propagation would be very large. Okay, so if function has a small derivative, then the error we make in the floating point representation doesn't have a serious implication, a serious replication. Okay, that's what we would see. Then the question we looked at was how do we extend this calculation into functions of more than one variable. So in that case we could again have a Taylor series in two variables. We have an example here of two variables. So there is a Taylor series in two variables. Okay. Look at that, this is very similar to what we did for one variable. So now we want to evaluate it at some point I plus 1 of two variables u and mu here. Okay, so u and nu. Okay, there are two variables, and these two variables are to be evaluated at some point I plus 1. So let us say there is a discrete set of points, and then we know the function value at some other point. Okay, that is close by. So we assume that ui and ui plus 1, the two different approximations of the variable u, and vi nu I and nu I plus 1 are two different approximations of the variable I plus 1. And we assume these two approximations are very close to each other, and then we can take the function value at nu I and ui and then expand it around that. So that is the derivative of the function with respect to u multiplied by the difference in the approximation, and the derivative of the function with respect to nu and the difference in the approximation. So if there are, that is a first order term, and the second order term there are three, because we have second derivatives, right. Second derivatives, there is a second derivative of f with respect to u, and second derivative of f with respect to nu, and a cross derivative. Okay. So there are three terms here. Okay, so you can see that now it is very similar to the function of one variable. The only thing now there are since two variables. So if even if the function is well behaved, in the sense it is not well behaved, it is even if it is a very small derivative with respect to one of the variables u, if it has a large derivative with respect to the other variable, it could have still large propagation of error, because we also have cross derivatives here. Okay. But the first order, it is what we keep is again only this term. Okay. So we will have f with derivative with respect to u and a f derivative with respect to nu. So that is what we would see. Okay. Now we could write this then delta f as derivative with respect to u and derivative with respect to nu. Again we take the mod, because we are only interested in the total maximum derivative. So the relative sign is also not important. We are interested in the maximum error possible, maximum error that is propagated. So hence we take here the mod of both and then sum it up. Okay, so the error in one plus the error in the other one does not cancel each other. It's an error. So it has to be taken the mod and the sum, the normal error analysis routines. Okay, so here, so this is the derivative and this is the errors in the two variables which we assumed. Right. So now we can generalize it further and write it for n variables. Okay, then we would write it like this, right. So we have a delta f into approximations in variables up to n variables, and each of them approximated by the corresponding tilde variable. Okay, so x1 tilde, x2 tilde up to xn tilde. and then we have the derivative as the derivative of the function with respect to each one of these variables. Okay, that is what we saw. Okay. So, we could actually look at the further implications of this. So, we saw that there are floating, because of the floating point representation, there is some errors, okay, which is introduced into the program. And we saw that this error can propagate depending upon what the nature of the function on this variable is. So, now the question is, if you are doing a series of calculation with this, okay, so how do we kind of quantify this? How do we say that this particular calculation is not viable, okay, because the error, as it will not be possible to do this particular calculation because there will be too much errors in this thing and the answers will be unreliable. So, how do we make a quantitative estimate of this, and how do we classify programs or calculations which are doable and which are not doable? Okay. So, that is what we try to do in the next section. Okay. So, we do this through this two definitions, one is stability and other is condition. So, let us look at what the condition means. Okay. So, a condition here, this is a definition, which is doing a definition here. The condition of a mathematical problem here, in this case a numerical problem, okay, relates to its sensitivity to changes in the input values. So, we will have to make a quantitative, we will have to make some, we have to define a quantity which would actually tell me what the condition of this is. We will do that in a few examples. So, if there is a particular step, a particular mathematical operation which is pretty crucial into the calculation, okay, and it is extremely sensitive to the input values to it. If you want to calculate a function f and evaluate it at some value x, and if it is extremely sensitive to the value of x which is given to it, okay, then that will be, we would say that that is an ill conditioned function or ill conditioned problem. That is what you have to look at. So, and then stability is that a computation is numerically unstable, okay, if the uncertainty in the input values is grossly magnified by the numerical method. In the dynamical systems kind of language, one would quantify this with something called Lyapunov exponent, etc., which is basically saying that if you introduce a small error at one point, okay, so you take a particular function and make two different approximations of that function, or you take a particular function and put an input value to it, x, let us say f of x, and x as we know is approximated, and we take two close approximation to the real value of x. Okay. So, x is a real number, and let us say, and we have floating point representation, and we have two different approximations of that, and we put that into this function, and then look at as we continue the calculation, okay, as continue the calculation, how does these two function values vary. Okay. Let us say we have a series of calculation to do, okay, and we start with some f of x, okay, and we are making these two different approximations to x. Okay. So, we are starting from slightly different points, and the question is, as we continue the calculation, the answers we obtain, how close they remain, or do they actually go away from each other very fast. If they do go very fast away from each other, then we say that it is not a very stable routine, because the small changes in the input would get amplified as we go further down. Okay. So, that is the stability of the routine. So, there will be an unstable routine. It will be almost impossible to do that particular calculation on a machine which has a finite number of precision, a finite precision. Okay. So, we would see those things in using some examples here. Okay, so let us quantify this thing. So, we just saw that we could expand, if you have an approximate variable, we could Taylor expand the function around the real value, around the approximate value, and quantify and get a difference f of x minus f of x tilde. Right. Okay, so, now the question is, we will take the relative error. Okay, so, we will take f of x minus f of x tilde divided by f of x. So, that will be the relative error, and by the Taylor expansion method we would say that it is f prime of x tilde into x minus x tilde by f of x tilde. So what we have done here, we saw in just few minutes back that f of x can be expanded around f of x tilde, and it will be f of x equal to f of x tilde plus derivative of f at x tilde into x minus x tilde. So f of x minus f of x tilde is simply up to first order approximated as f prime, that is the derivative of f with at x tilde into delta x, and we approximate this f of x by f of x tilde here in the denominator. So that is a relative error we will be approximating. Similarly, the relative error in x is given by x minus x tilde by x tilde. Okay, so then we define a condition number, okay, as basically the ratio of this, okay, that is the relative error in the function divided by the relative error in the variable. So how if I have an error in the relative error in the variable, how much that gets amplified when I evaluate the function, right? So that is a condition number. So you can see that if I divide this by this, I would get that. Yes, I get x tilde into f prime of x divided by f of x tilde. That is a condition number. Okay, that is an important quantity. Any step, any program which you run and you find that you are getting stability problems, the first thing to look at is the condition number for each of the steps involved, okay, and see how sensitive, how bad it is. What do you mean by bad? If I said this is a ratio of this relative error in f to the relative error in x. So if the ratio is greater than 1 or close to 1, then you know that this is bad. Okay, if it is less than 1, then it is good. Okay, that is what we would see. Let us look at a few examples and see how this is calculated. Okay, so it is summarized here that the condition number provides a measure of extent to which the uncertainty x is magnified in the function. Okay. So a value greater than 1 would tell us that the function's relative error is amplified, and a value less than 1 tell us that the relative error is attenuated, right. The functions with very large values are said to be ill conditioned. So this is a definition. What do you mean by ill conditioned? That if you are asked to calculate the condition and classify operations involved in a program as well conditions and ill conditions and conditioned, then this is what you would calculate. You would simply calculate f x tilde f prime of x divided by f of x tilde. Okay, so here is an example. Okay, so let us say we want to compute square root of x. So we have the function x as square root of x, and now we have an approximation for x, and the question is how does it get amplified, or how does it reflect on the function root of x, square root of x. So what is the derivative of f of x here? It is 1 by 2 root x. Right? So what was the condition? The condition is f prime of x into x by f of x. Again, mod, we are only interested in the absolute value of that number. Okay, so that will be 1 by 2 root x divided by root x into x. Okay. So we would get that as 1 by 2. So we have f prime of x into x divided by f of x. Okay. So f prime of x is 1 by 2 root x, right, and f of x is root x. Okay, so it's like x by 2. Okay. So for value close to 1, so you would get that as, sorry, this is 1 by 2. So if you have values, for any value of x, we have this error condition as 1 by 2, which is less than 1, and hence we would say that it is pretty well conditioned. Okay, so it's not bad. Okay, so any approximation you make in x, so you don't have to worry when you compute square root of x, because it's always less than 1. The condition is less than 1. Okay, so it's well conditioned. So let's look at another problem. So here I have a function f of x which is 10 by 1 minus x squared. Okay, so again we have to compute the derivative multiplied by x, okay, and divided by the function itself, right, and then that would give us as 20x by 1 minus x square the whole square divided by 10 by 1 minus x square, that is a function, the derivative and the variable x multiplied. Okay. So, that gives us 2x squared divided by 1 minus x square. Okay. So, now you see this again mod of this function. So, it is 2x squared divided by mod of 1 minus x squared. Now, this particular function, it looks like the condition is a function of x, the condition itself is a function of x. So, it depends on what the x value is. Okay. So, for example, x value close to 0, this seems to be pretty good, because the denominator will be close to 1 and this will be numerator will be close to 0. So, the condition number will be very small. Okay. So, that is good, well conditioned. But when you have x going close to 1, so you have the denominator going almost close to 0, and then you have this condition number very large, and that is a very bad thing. So, that means this is quite ill conditioned for variable values close to 1. Okay. Again, look at x larger than 1, when x very large, okay, much larger than 1, okay, then this denominator again goes to, because it is a mod we are interested in, so again goes to very large value. So, the condition would not be too bad. Okay, we can actually say that it is still not very good, but it is not too bad. We could say x very large, we could say that this can be approximated as x square itself, and then it will be just 2, it is still larger than 1, I agree. But for x going close to 1, this could be extremely large. So, this is very ill conditioned, and we should avoid steps like this in a problem of which is sensitive, okay, that is which tends to be unstable, which is sensitive. If a problem down in a program, the mathematical operations down this particular operation is sensitive to what goes into that, then this is a bad thing to do. That is what this condition tells us. Okay. So, the condition is a quantity which we should compute, okay, whenever we want to know what would be the crucial step, okay, which would determine the error of the program, total error in the program. If you want to really analyze a program and see what is the crucial error making step, okay, then we should compute the condition of each of this step. Okay. So, that is what we have done here. So, we have an operation like this, then it is sensitive to the value of x. Okay, so here is another example. The condition of the function f of x is equal to, we just actually look at this. Okay, so the condition of the function f of x is equal to 2 root of x plus 1 minus root of x. Okay. Let us look at this function. So, for large value of x, this function, so let us look at the condition. So, it is f prime of x into x by f prime of x. So, that is x into 1 by root of x plus 1 minus 1 by root x divided by root of x plus 1 minus root x. So, that is x by root x into root x plus 1. Okay. So, we can say that this is again of the order 1 if x is large. Okay. And so, the condition number is not really large, right. So, this is a kind of counter example which I want to give you. Okay, if x is very large, I could say that x plus 1 is close to x. So, and then I have root x into root x, and that is close to x, and then x by x is 1. Right. So, condition number is not very large, it is close to 1, but it is not large. So, we should think it should be okay. So, if you try to compute, use this thing, okay, using a number like 12682, I just took some number 12682, the function, and I evaluate this function, okay, and I keep some 3 decimal places after the thing. So, I have total number, I have total 1, 2, 3, 4, 5, 6 digits. So, if I keep it 6 digits and if I compute this, okay, I will get 0.008 as the answer. Okay. Right. So, this is kind of rounded. Okay. So, rounded to 3 digits after the decimal point. Okay. I have 6 digits I kept here, and then I have rounded to 3 digits after the decimal point. I will get 0.008. That is the number. The correct answer turns out to be 0.00887968. That's the error we have here is about 10%. Correct? Okay. Even though the condition is not too bad. So that's what we would see. Okay. So one way, so the best way to compute this is not, evaluating it as root of x plus 1 minus root x. That's what it means. Okay. Because even though the condition is good, okay, you have a large error. This is a counter example. So you say x is, the condition is close to 1. Okay. So it's not too larger than 1. So it's okay. That's what we would think normally, but here is a case where that is actually not very much true. So then what is the reason for this? Okay, so let's try to analyze this thing. Okay, so we have different steps. I have also a program here, so we can just look at this program. Okay, so that's the program. Okay, so we have this program. Okay, so what we have a function, a variable x, okay, and then these are the steps involved in the program, right? So we have x1, I called a variable x1. I have defined all of them as, okay, that's only a main program, no subroutines, okay, no functions. So I have defined as variables using floating point. Okay, this is floating point variables, a y, x, y1, x1 and f, and I have this number x as 12682.0. That's a floating point number. Now what do I want to compute? I want to compute root of x plus 1 minus root x into 2. Okay, that's what we want to compute. So what are the operations involved? The first I have to compute the root of x, okay, and then I have to compute x plus 1 and then take the root of that. Okay, so I call this y and I call the square root of that as y1. Okay, and then I have to take the difference. So there are these 3-4 steps involved. Okay, so there is, and then but I am just printing out that. Okay, so what is the value of that is, and you see that, and what you get if I run this, you would get so if I run this, I would get it as the following, right? So I get, so I am just printing out the number, okay, its root, the number plus 1 and its root, okay, and then we take the difference between these two, and that's the answer. Okay, that's the answer which you get. Okay, so the problem is that when you approximate it here, okay, so you can see that actually if I do this on this machine, okay, and I already get it as 0.008881 is the difference. I am computing it in two different ways, both gives me roughly the same answer. I just compute this, as you can see, using two different ways. So one is using a function called power, okay, and other one is just this using the function called square root, okay. And you can see that there is already a difference in these two. Okay, this is 0.8881 and this is 0.8880. Okay. So there is already a difference in this two methods, okay, which if you are interested in very small numbers, it's not very good because we have an error of in the 6th decimal place already, by just using two different functions to compute exactly the same thing. So you can see that if I use a 6-digit number here, okay, I'm going to get a large error. Okay, so that's because I am assuming I'm assuming this 1.112618 by 112618, okay, and 112614388 as 112614. So I'm just chopping off these numbers here. Okay, so there's error introduced in that, and the error is as bad as 10%. Okay. So that's the point which you are trying to see. So I think even though the condition is pretty good, okay, for the program is good. Okay. So now the question is what? So we again summarize that the number of steps involved. I have the function, the variable plus 1, the square root of the variable, the square root of x0 plus 1, and both these functions, and then the difference between these two. Okay. So now, and what we're going to do is we are trying to look at something called an error propagation. Okay. So that's what we wanted to look at now. Okay. So we calculate the error that's propagated in this step. Okay. For example, let's take the 4th step. Okay, that is this one. Okay, I named them as 0, 1, 2, 3, 4 here just to tell you what are the steps involved. I call the 0 step, the first step, second step, third step, and the fourth step. So the question I want to answer is, what is the error propagated to the fourth step because of an error I made in the third step? Okay, let's look at that. We will try to see how to compute this. Okay. We know how to define condition, right? We know if it is, we just saw some time back, how do we define condition? The condition is defined as the variable x into f prime of variable divided by f for a particular function f of x, right? So we'll just use the same thing here. Okay. So what we are going to do is to compute error propagation. Okay. What we do is we take this fourth step as our function. So we'll take this as my function x4. The fourth step is my function, and what is the variable here? The input to this variable is x3, the third step answer. Okay. So third step answer is the input to my fourth step. Okay. I hope you get this clear. There are 4 steps involved in this calculation, and I am trying to calculate the error propagated from one step to another. Okay. And what I want to do is to compute the error propagated to the fourth step, or the sensitivity of the fourth step, okay, because of the error in the third step. Right. That is what the error propagation which you would say. Okay. So I will take this as my input variable. Okay. I will call as t or something like that. Okay. And this is my function. So I will have a function some number minus a variable, and I look at the sensitivity of this or the condition of this with respect to that variable. Okay. That is what we would look at. Okay. So we are going to call that as some x2 minus t. Okay. I have defined this function as g of t x2 minus t. Okay. So remember, this I am going to call t. That is my variable coming in from the previous step. Okay. And this is my function. Okay. So that is what I am going to call, and I am going to compute the sensitivity of this function. Okay. So what is the f prime of this function with respect to t, right? Because I want to look at the sensitivity or the stability, the condition with respect to t. Okay. So the variable is t here, and we want to look at the condition of that with respect to t. So derivative of g of t, the g prime would be just 1 mod of that, we are interested. Right. And then we want to multiply it by the function, the variable, that is t. So you remember, it is g prime of t into t divided by g of t. So g prime of t is 1 and minus 1, g of then into t, and mod of that is t, and divided by x2 minus t. That is what we want to look at. So now the point is, if you look at the previous step, the difference between these two are very small. Okay. So that's a point here. Okay. So the x2 and the x3, the difference is very small, right? Right. So what we see here is the difference is small, so this particular step is bad. Okay. When x2 and t is close to each other, this particular step is bad. Okay. So hence we have a large error possible. So let me summarize this again. So what I am trying to say here? I am trying to say is that if you look at the function f of x itself, okay, as one function, and look at its condition with respect to x, okay, we find that this is pretty okay. Okay. We find that for x large, this should definitely be not too bad. But we write that down into a series of mathematical operations and look at the condition of a particular step, which is the last step, okay, and then we see that it is bad. So this actually tells you that what is important is not just a function, which we have to actually see how that is implemented in a program. What are the series of operations which is carried out, and then look at each of them, each of those series of operations. So I would, if you give me this kind of a function, then what I would do is I would actually multiply and divide this function by root x plus 1 by minus root x. Then I would get in the denominator it as root x plus 1 plus root x, and the numerator is just 1. Right? I will multiply and divide this function by root x plus 1 minus root x. It should not change the value of the function. Right? And at the same time, you would see that the condition is completely different. So that's something which you should try to see. So here is an example of a function which has good condition with respect to x, but on the way somewhere it has a problem in this step. So we should try to avoid that step, that is the subtraction between of these two numbers which are close to each other, and that is the one which is causing trouble, so we have to avoid that. Okay, so one way to do that is multiply and divide that function by root x plus 1 minus root x. To summarize it, so we saw that there is a problem with this computation, that is it is sensitive to the number of digits you have, and then the reason for that also we saw is because of this particular step in which we actually subtract root of x plus 1 root of x from root of x plus 1 when x is a large number, and this step introduces a large error because of the laws of significant digits. And we also saw that by looking at the condition number, that is the condition number was for that particular step was t by x2 minus t. So when t and x2 are close enough, that is when they are large and but they are similar numbers. In this case it was x2 was root of x plus 1 and t was root of x, so they were very close, so it's a similar numbers because x itself is a large number. Okay, so in that case this becomes a very large number, and that's the reason we saw is that this is a large amount of error. So this kind of analysis also helps us to correct these things in this kind of steps in the program. For example, we could do multiply and divide this f of x, which was root of x plus 1 minus root of x, by root of x plus 1 plus root x. So that wouldn't change the function value, okay, but the way the function is written will now be, instead of root of x plus 1 minus root x, it will be 1 by root of x plus 1 plus root x. Right. So following the earlier analysis, okay, so what we did for this, now we will follow the same thing, just the same analysis to see how the condition number of this particular function is. Okay, so we had x equal to x0 as some 1 2 6 8 2 as a large number, okay, and then we had to compute root of x plus 1, root of x1, okay, so that's it, x1 as x0 plus 1, and then we had root of x1, and then we had another step which is root of x0, and then we subtracted these two. That's what we had done earlier, root of x1 minus root of x0 as what we did earlier. So instead of that, now we will do 1 by x2 plus x3, right. So we had x2 minus x3 and we did the analysis with respect to x3, that, and now we do this here 1 by x2 plus x3, and then we look at the error propagation or the condition number for this step from 3 to 4. So then we write the condition number as, in this case, x3 multiplied by f prime, that is the function, the derivative of this function with respect to x3 divided by the function, and that will give us, now if you use this function instead of root of x plus 1 minus root x, we use this function, then that will condition number will turn out to be x3 in mod of 1 by x2 plus x3. Right. So which is much smaller than x3 into 1 by x2 minus x3, which is what we got earlier. Okay, so we use this x3 as t in that case. So this is much smaller than this when x2 and x3 are large and they are close to each other, the values. Okay, and then this number would be very, very small compared to what this number is, which is very large, which is the x3 divided by 1 by x2 minus x3, which is a large number. Okay, and you can also see this in a program. Okay, so now I will show you this program which will actually reflect this thing. Okay, so here is the program which actually computes this x is now defined as 1 2 6 8 2, and we are taking the square root of x, right. So that is, and then we have y here as x plus 1, and we take the square root of y. Okay, so you have square root of y, so y1 minus x1 is also square root of x1. The function was 2 star square root of x plus 1 minus square root of x, and now that's given by this particular function here f. So and I print that function f, okay, and then the other way of doing it is, which we just saw, is to multiply and divide it by y1 plus x1. Okay, so that would give us y1 or 2 by y1 plus x1, that is 2 by root of x plus 1 plus root of x, so that is just this function. Okay, so that is this function here. So we do this two different ways of thing, and then we will just run this program and print out. Okay, now we are using all variables are declared as float, that is single precision variable, and we look at the value of f and this 2 by y1 plus x1 and see what we get. So when we do that, okay, so we see that the value which we get, so I am using this E format. So when we write, so remember what we are doing is we are writing out f, which is y root of x plus 1 minus x1 root of x, okay, and this is 1 by root of x plus 1 plus root of x. Okay, so that is the two values which you are printing out here. Okay, so this is, so one value gives us 0.8806 10 power of minus 3, and other gives you 0.879685 10 power of minus 3, and this is closer to the this one is closer to the correct answer than this one, okay, which is now off by off in the third decimal digit here. So now we can also, I should also like to point out that this is this comes because of loss of significant digits. So we can also improve this by keeping more digits, okay, in our computation. That is, instead of using float, let's use double, okay, and then let's use double and then do the same computation. Okay, now we see that both these methods give exactly the same answer. Okay, so this is also an evidence that what the error we saw earlier, that is in this particular case, this difference between these two numbers here, which is the same function computed in two different ways, right, it actually comes from the loss of significant digits. So that's what we see. Okay, so now let's just summarize. So how do we get the total error in different operations, which is important, which we just saw that each operation is important. Okay, so if you have the error in a summation, then you have error adding up in these two. When you have subtraction, again the error adding up in these two. Again, remember this, we are not interested in the in between sign, we are looking at the total error. So total error is the sum of these two, and the multiplication, it depends on what the function itself is. Okay, so the value of that variable itself is, okay, so that is what important. Okay, and in the division you would have again similar one, so that you have the value of the variable itself is important to find out the total error in the function. Okay, so now we could actually look at as a problem, look at the function f of x as e to the power of x. So two things you have to look at. Okay, one is the previous step which we saw, that is how do we compute this differently such that the error can be slightly minimized, okay, or changed, or how do we avoid this particular step of subtracting each other. Okay, and then another thing you could look at, how do we compute a function f of x as e to the power of x using a Taylor series, and what will be, how do we estimate the errors in each of the steps. Okay, so these two things which you would now look at. So we saw two different functions which are ill conditioned right now. So we saw one function which is f of x, we said 2 times root of x plus 1 minus root of x. So that's one function which we saw and which we looked at, and then we found that it has, so we said the steps which involve in one of the steps, that is the steps which involve the taking the difference between this, is ill conditioned, even though the function itself is conditioned by with respect to x. So one way, how do we compute this in a better way? So one way is to avoid that step. Right? So remember the problem was in the last step, which we wrote it as we said x4, that is we said x2 minus x3, and we had said x2 is root of x plus 1 and x3 as x to the power of half. Okay, so we had these 3-4 steps. Okay. So this is the one which had problem with the the step. So the way to avoid this particular step. So how do we do that? Okay, so we can do it in the following way, that we would say that this function f of x, now I would write it as 2 times x plus 1 to the power half minus x to the power half divided by x plus 1 to the power half plus x to the power half multiplied by x plus 1 to the power half by x to the plus x to the power half, right. So I could do it this way. Okay, so then I have it as 2 times x plus 1 minus x divided by x plus 1 to the power half plus x to the power half, so that I have it as 2 divided by x plus 1 to the power half plus x to the power half. So now you can see that I'm doing the same computation, but I have avoided taking the difference between these two numbers, which was the problem when x is large. Okay. So when you're taking the difference between two numbers which are large, and I want to take a number, the difference is small. Okay. So the taking difference between two numbers which are large by itself is not a problem. The problem is when the numbers are large and they are close to each other, then you lose precision. Okay, that was the problem. Okay, so one way to do that is to just avoid it, taking the difference, and we can do it by this way. Okay, so the small changes like this in a step would change the reliability of the program considerably. Okay, so one could then compute what would be the stability of, or what the condition of this function itself is. So that's what we can look at. So now our function now changed to f of x is equal to 2 divided by x plus 1 to the power half plus x to the power half. Now how do we compute the condition? The condition is, we just saw, the condition would be, the condition number is f prime of x, right, into x divided by f of x mod, right. So that's, so f prime of x we can compute here. So f prime of x here is 2 divided by x to the power half squared, right, and then we take the derivative of that function, and then you would get it as, we are not interested in the signs, we are only interested in the total value of the function. Okay, so we have that, so we have the evaluated, and then you have to find this condition, and you could evaluate that at x equal to we said x equal to 1, 2, 6, 8, 2, and then you could look at what the condition is. That's one problem which we discussed. Okay, so you would see the condition of this and compare that with the condition of this function. Okay, so the condition of this function compared with the condition of this function, which both exactly the same. Okay, that would be interesting step to look at. So another thing which another problem which we discussed, which also is to be carried out, is to look at the function f of x, which is e to the power of x. Okay, f of x as f of x is equal to e to the power of x, and then use a Taylor series for this. Okay, for large x. So f of x is equal to e to the power of x, and you want to compute this at x equal to 12, which is large value. So to compute e to the power of x for x large value, that's something which you want to look at. Right? So we could write f of x as 1 plus x plus, right, x squared by 2 factorial, etc. Okay, and then compute this for a large x value. Okay, and then you could see what the error which you would develop is. Okay. So you could remember that you could also compute this function f of x by 1 by e to the power of minus x. We had seen it in 2 classes before that these two functions would have a large difference. Okay, so you could compute this as what e to the power of x and what 1 by e to the power of minus x, right? And then look at the condition of the function and the stability of each of this, or the error propagation in each of the steps. Okay, remember, just to remind you of what I mean by error propagation is this particular thing I can write it as many steps. Okay, so I would say step 1 would be to actually write 1 plus x, right. So that is step 1, and then step 2 would be to write it as step 1 plus x squared by 2. Okay, or you could introduce another step here actually if you are, so you could say that step 2 would be actually to compute x squared, okay, that is x into x, okay, and then step 3 would be actually to look at x squared by 2, and step 4 would be to look at step 1 plus step 3. Okay, so you could write it down in a very detailed series of operations like this, including each of these operations, okay, and then look at the stability of each of this. So now if I want to look at the stability of the error propagation from step 3 to step 4, then I would write this as a function of t, and then I would substitute this value here, so step 1, that is 1 plus x, some value there, and then I write the step 3 function as t there, right, that is what we saw. Okay. And now this would means that in the step 4 I am taking this as my variable and I am looking at the condition of this step with respect to this variable, step 3. So step 3 I have taken as t here, and then I would write this function as g of t in 1 plus x plus t, and then I will look at the condition number, condition as t into g prime of t, that is derivative of g with respect to t divided by g of t. Okay. So you can do this for different steps for this function as well as this function and see what the differences which you get is. So far we have seen programming methods and techniques, and also some of the points at which errors can creep in into the into a program, particularly into a C program. So now we look at some of the methods that is commonly used in scientific and engineering computation. Okay, so one of them is the interpolation of a given set of data. So the question comes, where do we use interpolation? So that is, suppose we have a set of discrete points xi and yi which are acquired let us say from an experiment or from a discrete numerical simulation. So then in some cases it may be required to find a value of y, that is, this is the dependent function y, okay, at a point which is in between two tabulated points x of I and x of I plus 1. In this case we need a function which would faithfully go through all the tabulated points, and then we can use that function to evaluate the value at a desired point x in between any two tabulated points. So that is the basic use of interpolation. You would need that for many things, maybe for finding derivatives or many other such uses. So one way is to construct, okay, so such a function is to use a polynomial. Okay, So we can, if you have n points, we can construct n minus 1th order polynomial which passes through all these points, and then we can evaluate the polynomial at the point x we want. So now this polynomial is that is, this is n minus 1th order polynomial which goes through these n points, is a unique polynomial, even though we can write this polynomial in various different ways. Now this unique polynomial will be called an interpolating polynomial. So that is what the next section of this course would look at, that various ways of constructing this polynomial. So now given this n points xi and yi, how do we actually construct a polynomial which goes through all of them? That is what we would be looking at in the coming lectures. So before we do that, I just want to demonstrate to you a difference between an interpolating polynomial and a fit, because a fit is another way of modeling a data which is commonly used. So the difference between here this plot is try to demonstrate the difference between an interpolating polynomial and a fit. So this blue points which is up here is a discrete set of values which we have obtained, okay, and let's say from an experiment or from some numerical simulation or something of that order. And then you have this red curve, okay, which goes through all these points, okay, which goes through this point, okay, which doesn't touch all these points, but which actually goes through this data. Okay. Now that's an example of a fit. So we normally use fit, which we will see later in the program, later in this course, that how to construct these fits. But for the time being here, we understand that we need to understand what a fit means also. So the fit is just that is used when we know how the function is supposed to behave, and we want to know how good the behavior of we obtain in an experiment or a simulation compared to the expected data value, okay, and that's where we use the fit, okay, and then the fit is a function which is predetermined, and then we just look at how good that function is to model a given data is. Okay, compared to that, a polynomial is something which goes through all the points. Okay, so now you can see that this curve which goes through all these points. Now this one is a polynomial, okay, that goes through all the points. So at the interpolating polynomial and the function have exactly the same value at the tabulated points. Okay, in fact we use that condition to determine the interpolating polynomial. So that's a big difference between an interpolating polynomial and a fit. Okay, in the case of fit, we actually have a predetermined form, and we are looking at how good that form is to a given set of data, and then a fit need not go through any of the tabulated points. Okay, what it should do is to reduce the error, okay, of between the tabulated points and the function values at every tabulated x values, while an interpolating polynomial need to go through all those points, okay, and it should be exactly the same at the tabulated points. Okay, so now we will look at in the next lecture how such a polynomial can be constructed and what are the different ways of constructing such a polynomial, etc.